Dash lines are showing up again. So, yeah, I added depth on all of them, kind of like as a big batch file, did them all at once, and then I realized yesterday, it's like, oh, dash lines don't get depth. If you make them depth, they become solid. So once again, we talked about mirrors, and we got three types of mirrors. We got a flat mirror, a concave mirror, and a convex mirror. If you ever get them mixed up, think caving in on you, or vexing away from you. Like, you vex me, get away. So, concave. Once again, if you're determining whether something is real or virtual, real is wherever the light is. Virtual is wherever the light isn't. So, you make virtual images when you stare at a flat mirror because it looks like you're on the other side of the mirror. Like, hey, look at all them kids on the other side of the mirror. They're way in there. I once, it was a video arcade. There used to be places where you play video games. They were dark and there was big machines. And I was at a video arcade one time, and to make it look like the video arcade was a lot bigger, one whole wall was just a giant mirror. And I walked up to one time and I'm like, whoa, excuse me. They're like, oh, that's me. Because it looked like it kept going. I had never been there before. It was in an airport, I think, in California. Anyway, I was like, oh, wow, the whole room it keeps going. But our brain puts images behind a mirror, so that's a virtual image. Okay, so we covered this yesterday. Give me a thumbs up if you're comfortable with this stuff.
Bueno.
Bueno? Okay. Well, put your hand up and wave it around if you have a question. All right, cool. I didn't lose my switches this time. Here we are. Then we have our mirror equations. So again, I don't know why the F is not just given 1/2 R, but it isn't. For some reason, it's always shown this way. But the important thing to realize is if you have a radius of curvature for a mirror, your focal distance is 1/2 that radius of curvature. Now, what does that mean? If you had a mirror that looked like that, that is the radius of curvature, R. And half that distance is going to be the focal length, F. Does that make sense? So if you know the radius of curvature of a shiny metallic circle, then you know its focal distance. And once again, distance object is always going to be positive. Objects are always going to be real, so they're going to get a positive value. The F could be negative, depending on whether the focal distance is virtual or real, and I'll show you that in a second. And the distance image could be real or virtual depending on where it is. So if you had an image, so here, let's have an object, I'm just going to use an arrow. If you had an object here, this would be DO measured to the center of the device. Make sense? Now if your image was right here, this would be DI measured from the device. Cool? Now, is this F real or virtual? Take a guess.
Real.
It's real, because it's on the real side of a mirror. This is the real side of a mirror. Well, how would you have a virtual? How would you have a virtual focal point for a mirror? Exactly, if it was convex. So if you had a mirror where this was the shiny side, so this is the shiny side, and your object was right here, this would be DO, and it would be positive, but this F would be a negative F. It would be a virtual F. It would be a virtual focal point. Okay? Think about this for a second. The light converges on the concave side. If your object is not on the concave side, but on the convex side, then that focal point becomes virtual because objects are always real. Okay. Kind of weird, even when I'm saying it, it's kind of strange. Give me a thumbs up if you're kind of internalizing this. Some of you are like, okay. So, objects are always real no matter what. Okay? If you think, I'm going to put an object on the convex side of a mirror, light is going to illuminate the object's light is going to strike the mirror, it's going to reflect off the mirror, so whatever the object is, that's the real side. Which means, regardless of where the image is, that focal distance, which is always on the concave side, is in that case virtual. So objects are always real. If the object's on the convex side and the focal distance is on the concave side, that focal distance becomes a negative focal distance, a virtual focal distance.
That's why it's smaller.
Mm-hmm. Yeah, and there's a really cool simulation, even better than PhET. The PhET simulation's like, and I found one even better than PhET we're going to play with the next couple of days. Maybe, I think I want to do a practical lab before the simulation. But, okay, so give me a thumbs up if that makes sense to you. It looks like I got most participation. Okay, put your hand up and wave it around if you want to go over it again. Okay, so cool, moving on. Once again, magnification is a ratio of height of the image to height of the object, and the negative ratio of distance of the image to the distance of the object. I'm not going to explain why this is negative because you're going to figure this out in the simulation, why it is negative when you actually look at the objects and images and how they interact with different types of mirrors and lenses. So just realize that magnification is high over ho, but negative die over do. Hi-ho, negative die do. And I'm not going to explain why that is because you'll figure it out on your own. Let's move on. Okay, then we talked about refraction, diffraction. Again, in this class, everything is refraction. Everything's refraction. Okay, we're not going to do any diffraction at all because to talk about diffraction, we got to talk about some quantum effects that I don't want to deal with until next year. If you want to take physics AP, we'll talk about diffraction and we can talk about quantum effects. But right now, I don't want to deal with it. Okay, so let's go back to our cat and fish example. Once again, despite what you see in cartoons, you don't have any looking beams. The environment has to illuminate an object, light reflects off that object. So in this case, is the cat looking at the fish or is the fish looking at the cat?
Fish is looking at the cat.
The fish is looking at the cat. So the environment is illuminating cat, light is bouncing off the cat into the fish's eye. Now in this case, what's going on is light is traveling from a less dense medium to a more dense medium. Where is the light fastest? Less dense or more dense? Less dense. Exactly the opposite of sound waves. Sound waves travel fastest and more dense. So here we have, you can actually see the little V up here, but here we have V, and here, let's make this really elaborate. Here we have V, and here we have V. Okay? And then when here, the environment is illuminating the fish is sending its light beams to the cat sees the fish. Here, once again, big V, here we have little v. So, light, this is where things get a little weird, even though light is technically a one-dimensional phenomena, it has wave-like properties in all 3 dimensions. Remember, it expands and contracts and expands and contracts, or it's like a corkscrew. It's not really a sine wave, it's more like a corkscrew, or if you want to get really accurate, it's more like a balloon that's constantly being inflated and uninflated and inflated and uninflated. Does that make sense? We just show light as a sine wave because we like to write things on 2-dimensional surfaces, but not really that. So imagine, if you will, you're in a ATV, 4-wheeler. You know what I'm talking about? It's like a motorcycle with 4 wheels. You're puttering along, and you're on the road, no problem at all. And then you hit a patch of mud, but only 2 wheels catch the mud. What happens to your ATV? It turns into the mud, right? Because all of a sudden, those 2 wheels are now traveling slower than the other 2 wheels. Does that make sense? Yeah. Like if you were in a go-kart or a big wheel or a tricycle, same thing would happen. You're cruising along, and then if half of your wheels on one side grab something and encounter more friction, slow down, your whole vehicle is going to turn. Okay? And that's what happens with light. When light's cruising along, boom, all of a sudden, it grabs on, you mentioned imagine light is my eraser, and it's now two-dimensional. So it grabs on here, it hits something more dense, it's going to bend into the more dense medium. So here's one. Oh, the corner of the light hit the medium first, it's going to bend into the more dense medium. Make sense? And the opposite also occurs if it's more dense, and now this corner here is still in the more dense medium, this corner here is in the less dense medium, it's going to turn away from the less dense medium. Does that make sense? Now, if you're like me, and you can visualize what the light's doing, great. If you don't, just remember that if density goes up, angle goes down. And if density goes down, angle goes up. So here, light is going from a more dense medium to a less dense medium, so the density is going down and the angle is going to go up. The angle of refraction here is going to be larger than the angle of incidence here. In this case, the density is going up. You're going from air to water. If the density goes up, the angle goes down, and the angle of incidence will be smaller excuse me, than the angle of, the angle of refraction will be smaller than the angle of incidence. Okay. So how do you feel about this? Give me a thumbs up if you're like, okay, I think I can handle this. Put your hand up and wave it around if you have a question. Looks like most of you got it. Okay, so if you can imagine waves as two dimensions, great, as they strike boundaries or little go-karts. Or you can just remember that if the density goes up, the angle goes down. If the density goes down, the angle goes up. And what we're talking about is the incident angle to the refracted angle. The incident angle to the refracted angle. Okay. No questions? Let me move on. Okay, I have some pretty cool demos. I just thought I'd throw them up here. This is fun. This is my coin bank. This was given to me by a physics teacher about 6 years ago. So coin, you can play with this. To get the coins out of the coin bank, just slide the back off. And you get your coins out. It's just a coin bank. It's for putting coins in there. So you can give me a tip. Hey, way to go. These are also kind of fun. These are, you see those things at CC's Pizza, where you get the little toys inside. So the one down here is filled with water. The one down here is filled with air. And you can take a look at what happens when light goes from water to water, and what happens when light goes from water to air. You can also pull that one out to take a look. But yeah, it'll make a mess, but that's all right. So these are for you to play with. This is 2 pennies in air. This is 2 pennies in water. This is 2 pennies in air and water. And this is something else for chemistry. Okay. We have a number that we attach to a media that basically says this is how optically dense that media is. And it's called the index of refraction. It's given the letter N, or index. I don't know why it's called that. Anyway, it's given the letter N, and it's a ratio of how fast light travels in the media to how fast light travels in a vacuum. So in air, we usually just round down to 1 because air is so close to a vacuum. We just say it's moving at c. But when you encounter stuff like water or glass, the index of refraction is important. My classes wouldn't work unless they had a pretty good index of refraction. And the better the index of refraction, the lighter the classes can be. Because the higher your index of refraction, the less material you need to cause the light to bend. So Plastic is okay. Has an index of refraction in the neighborhood of 1.5. That's okay. Glass is better, has an index of refraction of about 1.7. So glasses work better than plastic glasses. However, there's new materials called polycarbonates that actually approach 2.0. Polycarbonates are really, really dense plastics, and they usually cost a little more, but polycarbonates approach about a 2.0, so you have to use less lens material to get light to move the exact same amount as glass. So that's why polycarbonates cost more, because they have to use less material. So, yeah. Isn't that lame? But anyway, water is 1.33. The numbers you're going to see a lot are water at 1.33 and glass at 1.6 or 1.7. Diamond is 2.4, which is why diamond is so pretty. It's not why it's rare. It's rare because of the diamond cartel, but it's pretty because it has a really high index of refraction, and I'll explain what that does here in a second. This is Snell's law. Snell's law is pretty cool. Snell's law is just ni sine theta I equals nr sine theta r. It basically says if you know the index of refraction of two materials at an interface, and you know their angle of incidence, you can calculate the angle of reflection, or any of those others. So this is the index material of the incident material, angle of incidence, index of the refracted material, and the angle of refraction. And this is what we're going to investigate tomorrow in lab. We have a really fun lab. We'll fire lasers through water and alcohol and gelatin and all sorts of fun stuff. Okay. Questions? Give me a thumbs up if you're ready to move on. Okay. Put your hand up and wave it around if you're not. Give me a thumbs down when we go over it. Total internal reflection. This is cool. Have you ever been in a swimming pool and you couldn't see someone like standing on the deck of the pool? Or have you ever been at a swimming pool and you can see someone just below the surface? Okay, just me apparently. Anyway, so think about this. You have a situation where if density of the material goes down, then the angle of refraction goes up. Make sense? So go back to our cat example, our cat and fish example. Okay, so imagine light's going from water to air, and this angle of incidence and the angle of refraction is given to us by this relationship. If the density goes, in this case, up, the angle is going, sorry, if the density in this case goes down, the angle goes up. Make sense? So if this is 10 degrees, this is 20. This is 20, this is 40. If this is 60, this is 90. And if this is 65, can this angle ever be larger than 90? No, it can't. So eventually you get to a situation where the angle is so big, the angle of refraction is larger than 90 degrees. And that's what happens with total internal reflection. Got a really slick animation for this. Okay. I can't see it on my screen. All right, good. All right, this is the angle in here. So in this case, the ray is going from a less dense medium to a more dense medium. From air to, well, let's just make it glass. Okay? Now notice what happens. You can see the angle of incidence and you can see the angle of refraction. The ray is going into a less and a more dense medium, so the angle is smaller. You see this? Now, this follows with what we learned. Let's look at the next scene where the opposites get in the case. Here we're going from, let me get this glass, just make it clean. Here we're going from glass to air. And look what happens when we change the angle. Eventually, the angle of incidence becomes so large that the angle of refraction becomes 90. And when that happens, you get total internal reflection. So density is going down, angle's going up. This is our angle of incidence, our angle of refraction. As our angle of incidence is bigger, eventually Snell's law tells us that the angle of refraction becomes 90, and all angles above that become reflected. The light can't escape. So, the thing that Aaron's playing with right now is an optical fiber. Optical fibers use a plastic that's very, very high index of refraction, sometimes glass, depending on who installs it. And the light goes in one end, but it can't escape because the angle going from the plastic to the air, that angle of incidence would cause an angle of refraction that would be larger than 90, and it gets trapped. Here's another one. That one I got on Amazon for like $6. This one I got in a catalog. It's called a light guide. So I put the laser in there. You see it kind of bouncing around in there? And it doesn't really even come out until the end. Because this is a material with an extremely high index of refraction, so the light just kind of bounces around in there. You see that a little bit? Now if I shine it through the side, it'll go through no problem, because that's 90 degrees. But if I shine it through the end, it just kind of ricochets in there. And it gets trapped until it comes out the other end like that. So that's total internal reflection. The index of refraction of the glass is so much higher than the index of refraction of the air that the angle of incidence would cause an angle of refraction to be larger than 90, so the light just gets trapped. Okay, questions?
When you pointed the laser through that tube there, why was there no laser pointed up at the ceiling?
Why did it come out the end?
Yeah.
Because the material isn't optically perfect. Because it's just made out of cheap plastic. If it was optically perfect, like the kind of stuff you'd want to send into space, then the laser beam would be popping out the end. But as it is, as it goes through the material, it kind of diffuses a little bit. Okay. So the angle of incidence that would cause an angle of refraction to be 90 is called the critical angle. So, and sometimes it's just given delta C, but theta C, theta I, that would cause total internal reflection, that would cause a theta R of 90 or larger, is called the critical angle.
You said that's the theta I that produces the theta R greater than 90?
Yes, exactly right. The theta I, the angle of incidence, that would cause an angle of refraction to be larger than 90 or 90 or larger, that we just call the critical angle. Okay, questions? Okay, waiting? All right. Good question. If you were in a swimming pool and light was going from, like you were trying to see someone, you basically see a reflection of the bottom of the pool. And if you got really low to the swimming pool and you're trying to see someone in the pool, all you'd see is a reflection of the sky. There's a really slick parabolic tub, I guess, is the best example. It's a glass tub full of water, and it's at the Exploratorium in Berkeley, California. and it's just water. And when you put your hand in it, your hand just disappears. You pull it out, it's like, hey, it's like you can like, okay, I can see the bottom, I can see the floor. But when you put your hand in it, your hand just disappears because of the curvature of the glass and the water and all sorts of crazy optical illusions. Really fun stuff. Okay, give me a thumbs up if you're ready to move on. Okay. Maybe my button's going, oh, I think my button is just dying. Come on, button. My face cracker. Fine, button. Oh, maybe I need to move the screen. Okay, thin film refraction interference. This is totally cool. This is what you see, that rainbow effect when you see oil on top of water. This is also the rainbow effect when you see from the back of a DVD or a Blu-ray. Remember these discs that they used to store movies on? So you can actually see the rainbow effect on a CD or a DVD or a Blu-ray. And it has to do with thin film